I'm Wolfgang. I'm working at Menlo Systems since now even a little more than 13 years, and I'm basically occupied with developing frequency cones. Maybe you should ask, what is not quantum physics? Because basically all nature around you is quantum physics. The question is, why, if quantum mechanics is everywhere, is it not so visible, and how can we render it visible? Very known is the laser, but also all the semiconductors, how they behave, are formed from quantum mechanics. So in principle that's very wide. What people think of quantum mechanics these days, if they say World Quantum Day, it's quantum technologies that try to isolate the quantum mechanic effects more and more into the details and render it useful. The frequency cone is, if you want to put it like that, the most expensive stroboscope in the world. And that's a tool of choice if you want to observe, for example, an optical clock. You have a light field that goes in and wants to integrate the fast-spinning electron, but you cannot see the oscillations. Now you overlap that oscillating field that goes towards the atom with that frequency cone, and you probe it again and again and again. And what do you render visible? If the light fields coincide nicely, they amplify one another. If they're against one another, light pulse, the signal is lower. And that is similar to illuminating a guitar string with a stroboscope. If you put atom into a state, into two states simultaneously, which have different energies, there will be an oscillation basically of the particle within these states, and you can see the speed with which it evolves. And that has already been done with the famous atomic clock. And there you basically observe a change of state with a frequency of 9 gigahertz, and everybody can count that, and that has been proven very reliable. Maybe you want a clock that rotates more quickly, then you can measure more precisely. And one thing that rotates much more quickly is optical frequencies. You use the same principle as for the atomic clock, but you optically detect what is going on. If you have a system where you have atoms that you can put into the different states, like for a clock, you could also evolve it on and put more of these particles next to one another and go towards a quantum computer, store information in it, compute inside, and then take it out. These are very complex apparatus because all this information needs to be protected from the outside world. That means the particles are stored somewhere, and you need to write information into it, get it out. And this is all done via lasers, because nothing else goes into the vacuum without perturbing it. And if you look at these experiments, they are rather complex. They have sometimes more than 10 different lasers, which all need to shine at the right moment with a correct color onto these atoms. And what we can do with a frequency cone, this pulsed light offers a spectrum which is very wide. It reaches from the infrared up to the ultraviolet. So if you build a frequency cone correctly, you can measure all these different lasers that you need for your experiments, stabilize them, and then shine them with the right frequency on your experiment. And you know the exact frequency down to the decimal place in hertz, what that frequency of the laser is. And that is fascinating to experimentalists. In the beginning, there's one single equation, and it doesn't look so complex. And from this single equation, so many different things come out. If you do physics these days, you always start from that same equation, and you apply it here and here and here. It's so diverse, you always go back to this one simple equation. Quantum is a summary of what holds the world together, but also how different things can appear from it.